Welcome to this explainer. Today, we are tackling an absolute monster of a math problem. For decades, the Collatz Conjecture, the famous 3x plus 1 problem, has teased mathematicians with its elementary school simplicity. The rules are basic. Take a number. If it's even, divide by 2. If it's odd, multiply by 3 and add 1. And no matter what, it always seems to loop right back to 1. Sounds super simple, right? Well, as anyone who has fallen down this particular rabbit hole knows, it has stubbornly resisted proof. Until now. Today, we're going to contrast that deceivingly simple rule with the staggering advanced mathematics of the Adelic Langlands framework that finally crushed it. We're going to get right into the equations that make this global architectural proof actually work.
To understand this mathematical marvel, we are going to follow a strict roadmap. We'll start with 1, lifting the system, then move to 2, front I, the solid core, followed by 3, front 2, the liquid domain, then 4, Fredholm factorization, and finally 5, the product formula constraint.
All right, let's jump right in. Section 1, lifting the dynamical system.
To prove something globally, we first have to elevate our perspective. When we look at the full Collatz transfer operator equation, notice how it acts as a translator. It literally takes that iterative, heuristic 3x plus 1 game and lifts it into a formal mathematical object. You've got distinct branches here. The even branch is represented by 1/2 f of 2x, the odd branch is f of x minus 1 all over 3, and this is absolutely crucial, we have the indicator function denoted by chi. So, you might think it's just an iteration. Actually, scratch that. It's now a unified functional-analytic object, and we can rigorously analyze its spectral properties.
But to move beyond simple guessing or manual crunching, we have to make a massive conceptual leap. We lift the entire system into the adele ring. This physically separates the mathematics into two distinct pillars, the prime two-adic place, where binary divisibility governs the system, and the Archimedean place, which is governed by magnitude expansion. It's truly fascinating. We are completely transforming a local arithmetic problem into a global one.
The architecture here defines the specific analytical spaces and critical bounds we absolutely must achieve to stabilize both halves of our bridge. On one side, we have front I, the solid two-adic core striving for uniform nuclearity. On the other side, front 2, the liquid Archimedean domain seeking a strict Crace-class ceiling. Both of these pillars must achieve truncation-independent stability to support the global Fredholm determinant. Let's start with building that first pillar.
Moving on to Section 2. Front I, the solid core.
This is where we secure the two-adic domain against any instability. The math here is just beautiful. We have a uniform geometric decay bound where the jth approximation numbers of our finite section transfer operator are strictly less than or equal to 2 to the power of negative j. What does that mean for us? It guarantees zero-order p-adic nuclearity that is completely independent of the truncation level n. In layman's terms, as we expand our matrix out to infinity, this geometric decay entirely prevents mathematical spectral leakage. The core remains totally solid. No leaks, no cracks.
Now, getting those bounds meant dealing with the messy, non-local carry bits of two-adic division. To pull this off, the framework relies on 4 specific mechanisms. First, the space framing in a weighted Mahler-Banach space, where the weight equals 1 ensures off-diagonal matrix entries are strictly contractive. Then it uses an exact indicator valuation, an odd branch convolution, and finally an even branch integral shift. You can kind of think of these as sequential filters. They catch and overcome the carry bits, preserving the absolute integrity of our solid core.
The visual representation of that decay shows a rigid geometric barrier forming a step-like structure. Everything above that line becomes a mathematically impossible region. This maximum allowed valuation ensures that no matter how far we push our infinite matrix compression, it simply cannot degrade the residual core. That first pillar, it is mathematically indestructible. Okay, on to Section 3. Front IV, the liquid domain.
Now that our solid core is built, we have to address the other side of the chasm, the Archimedean domain. We switch gears entirely here to a continuous domain. We map the dynamics onto the real numbers using a logarithmic coordinate change where t equals log x. We're now operating within a weighted Sobolev space with an exponential weight of log 2. The full operator becomes a weighted sum of the inverse branches, effectively mapping out the smooth, continuous magnitude expansion of the system.
By analyzing these branches, we can calculate a definitive, level-independent trace-class ceiling.
Let's follow the numbers. The even branch gives us a norm of 2. The nonlinear odd branch bounds at 16. With their respective weights, the full operator bound aggregates to 17. Then, by bounding the mixed Sobolev kernel, which gives us a factor of 2, taking us up to 34, and combining it with the nuclear embedding constant of 8 pi squared, we utilize chi-fan majorization to establish a definitive trace class ceiling for the entire operator.
So, what's the takeaway from all that math? It's this specific number right here, 2700. Our trace class norm is strictly less than 2700, and this isn't just a random value. It is a strict, mathematically unbreakable maximum bound that is completely independent of the truncation level n. This ceiling perfectly secures the liquid half of our Adelic bridge. And just like that, both of our pillars are fully stabilized.
Let's move to Section 4, Adelic Fredholm factorization.
We have our two pillars, the solid two-adic core and the liquid Archimedean domain. Now it's time to prepare the keystone to join them together. Because we establish uniform convergence and local nuclearity in both fronts, we can use Lagos field theory to assemble them. The factorization equation shows the Adelic Fredholm determinant, d sub a of z, formed by seamlessly multiplying the Archimedean determinant with the product of all non-Archimedean determinants. We can safely assemble the finite and infinite local determinants into a single, globally convergent object without any distortion at all. If a periodic Collatz cycle actually exists, it absolutely must be a simultaneous root right here in this equation.
Finally, Section 5, the product formula constraint. We are lowering the keystone into place to see if the Collatz cycle can mathematically exist under global rules. The universal Adelic product formula sets the ultimate constraint. Global arithmetic consistency strictly dictates that the product of all valuations over all places must equal exactly 1. If a hypothetical Collatz cycle existed, it would create a closed residual module of positive content. However, our frontists I and II prove that local residual cores possess strictly unit content at every single finite place.
Think of it kind of like a ledger on a balancing scale. On one side, we have an Archimedean phase discrepancy. On the other side, we have the finite place residual volume. But because our mathematical proofs establish that those finite place residual volumes are perpetually locked to unit content, they physically cannot compensate for the Archimedean discrepancy on this ledger. For finite cycles, compensation is just impossible. And for infinite cycles, well, Baker's Diophantine lower bounds ensure the ledger term exceeds any finite compensation.
The cycle simply cannot close. The overarching reciprocity of the Adelic bridge ensures that local residual cores are continuous and bounded. By applying this Adelic product formula constraint, the framework formally and completely unconditionally excludes the possibility of non-trivial Collatz cycles. The 3x+1 conjecture is finally, rigorously laid to rest.
And that right there is the true power of structural functional analytic mathematics. It completely replaces infinite guessing with unbreakable boundaries. But going through this incredible proof really makes you wonder, if the Adelic Langlands framework can build a bridge to solve the notorious Collatz conjecture, what other completely unsolvable mathematical mysteries will this exact same structural blueprint decode in the future? Thank you so much for exploring this math with me today.